So let's finish 1.2. So we have types of equations to identify, and then a couple of application questions, word problems. So types of equations. So we've solved different types of linear equations, right? Linear equations with no fractions, linear equations with fractions, right? So we call them rational equations. We did that in the last video. But now so we can identify types of equations, either as identity, conditional, or inconsistent. So what does that mean? So an equation that's true for at least one real number, so if it has at least one solution other than all real numbers, so it has to have at least one, but not all real numbers, we call this a conditional equation. The examples that we've worked so far, with exception of this last one, example 2, part C, because remember part C had no solution. All the other ones had at least one solution, right? So those are all examples of conditional equations. An equation that's not true for any real number is called inconsistent. So that's what type of equation this last one is that we did in the last video, part C of example 2. We ended up with x equals -1, but when we checked it, we realized it was not a solution. So this type of equation would be called inconsistent because it has no solution. And then the other possibility is an identity, an equation that's true for all real numbers. So if we could plug in any real number and the equation checks out, we call that an identity. So let's just do one example of each. So categorizing an equation. So example 3, let's solve and determine whether the equation is considered an identity, a conditional equation, or inconsistent. And then this is good practice too, solving an equation. So look at part A. So for A, let's distribute, get rid of parentheses here, right? That's going to be the first thing. So we're going to have, we'll do this one over here. So we're going to get 4x minus 7 equals, let's distribute the 4. So we're going to get 4x minus 4 and then plus 3. So we have 4x minus 7 equals 4x minus 1. So I combine the -4 and the +3. Now let's gather the x terms to one side and the constants to the other. So let's bring the x terms to the left. So let's subtract 4x from both sides. And then I'll do a different color. Let's add 7 to both sides. We'll bring the constants to the right. So on the left, I'm going to end up with 4x minus 4x, which is just 0. And then a -7 and a +7 is also going to be 0, right? So on the left-hand side, I have 0. And then on the right-hand side, I'm going to have -1 plus 7, which is equal to 6. So we haven't seen this, right, in the other examples that we did. We always had an x term, right, an expression that contained x on one side, and then we had a constant on the other. But in this instance, whenever this happens, if the x terms sum to 0, like in this case, or the variable term, if we're left with a statement that doesn't make sense, like in this case, 0 is equal to 6, that doesn't make sense, right? 0 is not equal to 6. This indicates to us that there's no solution. So there's no solution to this equation. And this would be an example. So an equation that's not true for any real number is called an inconsistent equation. So this is an example of an equation that is inconsistent because there's no solution. So let's look at B. So for B, I'm going to do the same thing. Let's distribute. So we're going to get 7x plus 9 equals 9x plus 9 minus 2x. So we're going to have 7x plus 9 is equal to 9x minus 2x is 7x plus 9. And I'm going to point out something at this step because you might not realize it. Look at the left-hand side and the right-hand side of the equation. You see how they're exactly the same? 7x plus 9 is equal to 7x plus 9. So think about it. We could plug in whatever we want for x. Like, what if x is 1? If I plug in 1 for x on the left-hand side, I'm going to get the same exact thing on the right-hand side, right? Because 7 times 1 is 7 plus 9, we'd get 16 equals 16. What if I plugged in 0 for x? I would get 0 plus 9 equals 0 plus 9. Those expressions are exactly the same. So this is an indication when you see something like this that it's probably going to be an identity where we're going to have any real number could be a solution to this. But look, let's finish solving this algebraically and you'll see what happens. So I'm going to bring the x terms to the left. So if we subtract 7x from both sides, and then let's subtract 9 from both sides. So we'll bring the x terms to the left, the constants to the right, and I'll continue up here. But look, 7x minus 7x is 0, a positive 9 and a negative 9 is 0. And then on the right-hand side, 7x minus 7x is 0, positive 9, negative 9, 0. So we end up with the statement 0 equals 0. But that is a true statement, right? 0 does equal 0. And just like I explained to you before in that previous step, we could plug in anything for x and it's going to make both sides of the equation equal, right? So your solution set is all real numbers. So any real number will work. And if that's the case, an equation that's true for all real numbers, we call that an identity. So this equation would be an example of an identity. And let's do one more. Look at C. 13x plus 14 equals 12x minus 5. Nothing to distribute. We don't have groups, right? We don't have anything to combine. So let's gather the x terms. I'm going to bring the x terms to the left. So I'm going to subtract 12x from both sides. And then let's bring the constants to the right. So I'm going to subtract 14 from both sides. So we're going to have 13x minus 12x is 1x equals negative 5 minus 14 is going to be negative 19. So we end up with one solution. X is equal to negative 19. And you could check that and make sure it checks out. But whenever we end up with an equation that has at least one real number for a solution, but not all real numbers, that's a conditional equation. So since we have exactly one solution, we consider this equation a conditional equation. So that is an example of each, an inconsistent equation, an identity, and a conditional equation. So let's move on to the last part of section 1.2, solving applied problems using mathematical models. So really, we're going to do what we were doing in the other example, solving a linear equation, but now it's going to be in an applied word problem. So we're going to apply this, look at a more realistic, equation that could, we could use to model some relationship. So let me just make this a little bit bigger. So look at example 4. It says persons with a low sense of humor have higher levels of depression in response to negative life events than those with a high sense of humor. This can be modeled by the formula D equals 10x divided by 9 plus 53 divided by 9. In this formula, X represents the intensity of a negative life event, and D is the average level of depression in response to that event. If the low humor group averages a level of depression of 10 in response to a negative life event, what is the intensity of that event? So let's look at this formula for a minute. Let's rewrite it. So we have D is equal to 10x over 9 plus 53 over 9. So this models depression, because D stands for the level of depression, depending on the intensity X of a negative life event. So a person's depression level, their average level of depression, is going to depend on how intense that negative life event is. And that's what X represents. So what we're saying is, if this low humor group averages a level depression of 10, so that's a value of D, right? D stands for the average level of depression. So if D is equal to 10, what is the intensity of that event? So you see what we're being asked to solve for? We're being asked to solve for, whoops, sorry about that. Let me just change this to highlight. What is the intensity of that event? So in other words, what is X? Because X represents, let me go back to highlight for a minute, the intensity of that negative life event. So what we could do is, if we're trying to solve for X, right, but we know D, I could replace D in this equation, right? So D, we said, is 10. So if D is 10, then that should equal 10x over 9 plus 53 over 9. And remember in the previous video how we were solving these rational equations where we have fractions. Multiply the numerator and the denominator by the common denominator, the least common denominator, which in this case is going to be 9. So I'm going to multiply every fraction in this equation by 9. So what we're going to do is we're going to distribute the 9. So we're going to have 9 times 10, which is 90, over 1, so just 90, equals 9 times 10x, which is going to be 90x over 1 times 9, which is 9, plus 9 times 53, which instead of multiplying that out, because that's a large number, just going to leave it as 9 times 53, over 1 times 9, which is 9. And now you'll see we could reduce, right? So 9 into 90 goes 10 times, and 9 into 9 goes once. So my equation is going to be 90 equals 10x plus 53. And look, no more fractions, right? And now we could solve for x. So if we have 90 equals 10x plus 53, we want to solve for x, right? So I'm going to subtract 53 from both sides. 90 minus 53 is going to be 37, right? Equals 10x. And then we want 1x, so let's divide by 10. 37 divided by 10 is 3.7. So x is 3.7, and that represents the intensity of that event. So the intensity level would be 3.7 in order for the average level of depression to be 10 in this group. And let's look at one more example. So it says a company wants to increase the 10% peroxide content of its product by adding pure peroxide, 100% peroxide. If X liters of pure peroxide are added to 500 liters of its 10% solution, the concentration, which we'll call C, of this new mixture is given by this formula. And that's just a rational equation, right? We have an equation, but it contains fractions. And we dealt with these, right? Just like the one above is a rational equation. So the question is, how many liters of pure peroxide should be added to produce a new product that is 28% peroxide? So remember, C is the concentration level. So we're basically being told, okay, if C is equal to 28% concentration level, how many liters of pure peroxide should be added to produce this new percentage? And X represents the number of liters. So X liters of pure peroxide. So that's what we're trying to solve for here. What is X if we want our concentration to be equal to 28%? So we're going to replace C in the formula with 28%. But anytime we're working with percentages in an equation, unless it's stated otherwise, we have to convert it to a decimal number. So 28% is the same thing as 0.28, right? We drop the percent sign and we move the decimal to the left 2 spots. So let's set C equal to 0.28, and that's going to equal X plus 0.1 times 500 divided by X plus 500. So now we want to solve for X. So I see that we could simplify the 0.1 times 500 in the numerator. That's just 50. So we're going to have 0.28 equals X plus 50 over X plus 500. Remember what we were doing in the other rational equations that we were solving. Anything that doesn't look like a fraction, just put it over 1. So I'm going to put 0.28 over 1. And now I have two fractions, right? 0.28 over 1, and that has to be equal to the fraction X plus 50 over X plus 500. Now a trick, whenever we have just two fractions set equal to one another, we call this a proportion. And an easy way to solve a proportion is we can multiply by the common denominator, but honestly, I just think it's easier to cross multiply and set the products equal to one another. So whenever we have a proportion, cross multiply. So look, if I cross from bottom left to upper right, I'm going to have 1 times X plus 50. Now set that equal to your other cross product. So 0.28 times X plus 500. Distribute, get rid of parentheses. So on the left, I'm going to have X plus 50. And then on the right, I'm going to have 0.28X plus 0.28 times 500. And we can multiply that out. So 0.28 times 500 is 140. So we're going to have X plus 50 equals 0.28X plus 140. And now we have to gather the X terms to one side and the constants to the other side. So I'm going to bring the X terms to the left. So I'm going to subtract 0.28X from both sides. And since I'm bringing the constants to the variable terms to the left, I'm going to bring the constants to the right. So I'm going to subtract 50 from both sides. So we're going to end up with, think of this as a 1x minus a 0.28x. That's going to be 0.72x. And then equals 140 minus 50 is 90. We want 1x, so let's divide by 0.72. So we're going to get x is equal to 90 divided by 0.72. and that's 125. Now, this is an application question, right? So remember what X stands for. We just solve for the number of liters of pure peroxide, right? We're being asked to solve how many liters of pure peroxide should be added so that the new concentration is 28%. And we got 125 liters. So units are important when we're working on application questions, so make sure you include your units as well. So this wraps up section 1.2. In the next video, we're going to start section 1.3, which is models and applications.